Question 4. A scientist cooled the air inside a container. The temperature of the air changed from 20 degrees Celsius to 0 degrees Celsius. The volume of the container of air stayed the same. Explain how the motion of the air particles caused the pressure in the container to change. Okay, so the pressure in the container to change as temperature decreased. So what's going on with the air particles? And it's worth 3 marks. So 1, 2, 3. Okay, so first thing is to describe. So describe what happened to the pressure. Well, pressure is the force per unit area. Okay, so it's the force exerted on the area inside something. And what happens is as temperature decreases, the pressure in something decreases as well. So think about the opposite is probably more easier. When you heat something up, the pressure increases. So if you heat a kettle up, the pressure inside increases, and eventually the gas starts to escape as steam through the spout. Okay, so the opposite happens here. So as temperature decreases, pressure decreases. Okay, then we need to say why that is. Okay, well, the reason is because the particles are banging around and they've got a lower kinetic store. So particles of air move more slowly as temperature decreases. Their kinetic store decreases. And because they're moving more slowly, what's happening is they're colliding less violently, less collisions or less force. So as particles slow, they collide with the wall of the container, the walls of the container, with less force. Okay, so pressure is related to how hard those collisions happen. The air contained water that froze at 0 degrees Celsius. The change in internal energy of the water as it froze was 0.7 kilojoules. The specific latent heat of fusion of water is 330 kilojoules per kilogram. Calculate the mass of ice produced and use the physics equation sheet, and it's worth 3 marks. So if we look in the physics equation sheet, remember we're going to use every, so we're going to write down the equation first of all. I'm get my little stick with every, so we can write what they are. Okay, so this is our little stick with every. First thing we're going to do is find the equation, and we're looking for this value here, specific rate of fusion, and that's 330 kilojoules per kilogram. The change in internal energy is that, and we've got a temperature of that. So we're going to find the equation that's got specific latent heat, okay, and mass, and it turns out that that equation is change in energy equals mass times specific latent heat. Okay, so that's the equation. Now if we've got that, it's actually E is equal to M, L is the symbol. I'm then going to put my values in and convert. Okay, so what do I know? Well, I've got water frozen at 0 degrees Celsius. Okay, we don't actually need that. The change in internal energy, so if I put delta there to mean change in, so delta E is equal to 0.70 kilojoules. Well, I don't like it in kilojoules, so I'm going to convert it into joules. So I'm going to times it by 1,000, because remember, kilo just means times 1,000. gives us 700 joules. And I've got L, which is my specific latent heat. That value is 330 kilojoules per kilogram. So I'm going to convert this as well into joules, so times that by kilo just means times 1,000. So 330, 1, 2, 3 zeros, joules per kg. Next I'm going to take these values and just pop them into the equation. So 700 is equal to M times 330,000. I then rearrange and solve. So 700 divided by 330,000 gives me a total value of, I'll just do it on the calculator, so 700 divided by 330,000 equals 0.21 recurring. Okay, so, oh sorry, 2.1, 2 point, oh no it's not, hang on, sorry, I've got that wrong. There we go, so 0.21 recurring, so it's 0.021, and if I just wrote down what it said in my calculator, it's got dot and dot. We never use the dot notation in science. Okay, so in this case I would round it to, if I look at the values here, the most significant figures I've got in any of these values was 330, so I'd round it to 2SF. So 0.021 to 2SF. Okay, we never use the dot notation in science.